Hello students, I am Praveen Kumar from ABS Engineering College, Ghaziabad. In this video, we will discuss about slip torque characteristics of a three-phase induction motor. Now, we all know the torque of three-phase induction motor is given by this relation K S E2 square R2 divided by R2 square plus SX2 whole square, where this E2 is the per phase rotor induced EMF at standstill condition. R2 is the per phase rotor resistance at standstill condition. X2 is per phase rotor reactance at standstill condition. S is the value of motor slip, and K is constant of proportionality, whose value is given by 3 divided by 2 pi ns, where ns is the synchronous speed of the induction motor in revolution per second. Now, from this torque expression, we can find out the condition for maximum torque. For this, we differentiate this torque expression with respect to slip and put it equal to 0. So on differentiating this equation 1 with respect to slip, we get in denominator, we get this R2 square plus Sx2 whole square and the square of total denominator. And at numerator, this denominator term as it is into derivative of numerator with respect to s. As so, what we get is k e2 square r minus numerator as it is ks e2 square r2 into derivative of denominator. Here, this in denominator, this r2 square is treated as constant. What we get is 2x, 2s, x2 square, put it equal to 0. On further solving it, taking this denominator, if we cross multiply, it reduces to 0. And on this numerator, taking this term common, k e2 square r2, what we get is r2 square sx2 whole square minus, here this s multiplies and we get 2x, twice of 2x2 square is equal to 0. Now on further simplification, this we get R2 should be equal to Sx2. Or we can say that torque in an induction motor is maximum at a slip which is given by Sn is R2 upon X2. This Sn is known as slip corresponding to maximum torque. This is a important value of slip, and this is the slip at which this torque is maximum. Now, as we have derived in previous slide that slip at which maximum torque occurs or slip corresponding to maximum torque is given by the ratio of standstill rotor resistance to the rotor reactance. And if we put this value of slip in this expression of torque, which is K S E2 square R2 divided by R2 square plus Sx2 whole square. So if we, in this torque expression, if we put R2 is equal to Sm x2, we get the value of maximum torque, and this Tmax is coming out to be, if we put R2, what we are going to get is K E2 square upon 2 x2 Newton meter. This is the value of maximum torque, and this maximum torque is achieved at a slip whose value is given by this relation R2 upon x. Here, an important point is this maximum torque is independent of rotor circuit resistance. So, with this, now we will discuss the slip torque or speed torque characteristics of three-phase induction motor. So first of all, before discussing the this curve, first let us discuss the scale of this curve. On x-axis, here we have plotted slip, and we all know slip and motor speed are inversely proportional to each other. At this particular point here, the value of slip is 1. Slip is 1 means the rotor, or we can say the speed of motor is 0 or motor is at rest. So in this particular direction, slip is increasing, means at this particular point, this motor is at rest, and as we move in this direction, here in this direction, value of motor speed is increasing. So on x-axis, we can assume that there are two different quantities. One is slip, which is 0 at this particular point, or at the beginning, slip is 0. And this is the maximum value of slip. Slip is 1 for this curve. 1 means motor is at rest. So in this particular direction, slip is increasing, and opposite to that, motor speed is increasing. As far as variation of speed is concerned, at this particular point, when value of slip is 0, we can assume that at this point, motor speed or rotor is actually running at synchronous speed. And at this point, where value of slip is maximum or 1, at this point, actually motor speed is 0, or we can say this is the beginning point where motor has to start its rotation. Now, this is the plot of variation of torque with respect to motor slip or motor speed. The entire slip torque characteristics can be divided into two regions. One is known as unstable region or high slip region. This high slip region basically lies from S is equal to 1 to S is equal to Sm. Sm is the slip corresponding to the maximum torque. Here, this is the maximum torque. At the beginning, the curve starts from this point B. This B represents the value of starting torque of the motor. So, in this high slip region, here, as the value of slip is close to 1, so in torque expression, as we know, motor torque is proportional to S E2 square R2 divided by R2 square plus Sx2 whole square. So as long as motor slip is close to 1, so in this denominator, this term Sx2 whole square is much larger than this R2 square. So in denominator, this R2 square can be neglected, and if we neglect this denominator term, we get in this high slip region or unstable region, the torque of the motor after neglecting this denominator term R2 square, the torque of the motor becomes inversely proportional to the motor slip, or if torque is inversely proportional to the slip, means it is directly proportional to the motor speed. So here we can clearly see that as the value of slip is decreasing, as motor is accelerating in this direction, so as rotor starts rotating from rest, as the rotor picks up rotation, the value of slip starts decreasing from 1. As the slip is reduces, the value of torque keeps on increasing up to this point where the torque becomes maximum. So in this entire region, torque is inversely proportional to the slip or directly proportional to the motor speed. This region is known as unstable region. This is because in this region, the induction motor cannot operate. Here, what happens is, as the motor speed increases, the corresponding value of slip decreases, and decrease in slip means increase in motor torque. And as the motor torque increases, means the RPM of motor further increases. So torque and speed both are directly proportional to each other. So the motor speed and torque, they are continuously increasing in this region. That's why the operation of motor is not stable. So this region is also known as unstable region. Now, the in this unstable region, as torque and slip are inversely proportional to each other, so the shape of this slip torque characteristics is uh, like rectangular hyperbolic in nature. Now, moving to the stable portion of the curve. So, this is stable region is also known as low slip region, which is shown with the solid line in this diagram. This low slip or stable region is actually lies from slip S is equal to Sm to S is equal to 0. This is the stable region. As we know, when motor reaches to S is slip corresponding to maximum torque or the motor torque reaches at its maximum value. So at this point, the denominator term as motor torque is S E2 square divided by R2 square S X2 whole square. So when value of S is equal to Sm, at that time in denominator, the R2 and Sx2 square both are equal in magnitude. So if motor further accelerate, the value of slip decreases, and as motor crosses its maximum torque and beyond this maximum torque, the value of slip is continuously decreasing, and now in denominator, the term R2 square becomes greater than Sx2 square. So in denominator, now the slip becomes too small that this term R Sx2 square can be neglected when it is compared with R2. So now, after crossing the maximum torque, what happens is now the torque becomes directly proportional to the slip and becomes inversely proportional to the motor speed. So in this entire zone, what we see that if the value of slip is decreasing, there is a corresponding decrease in motor torque. And that's why as slip and torque are directly proportional or torque and speed are inversely proportional to each other. That's why in this region, the operation of motor is stable in nature. So normally induction motor operates in this zone. Here, what happens is if we connect load on the motor shaft, the as the load connected on the motor shaft, the motor speed decreases. Speed decreases means the motor slip increases, and with the increment in slip, the motor torque also increases. So the additional torque requirements are satisfied. So in this region, the torque and speed, they are actually opposite to each other, and that becomes that's why the motor operations are stable in nature. So normally induction motor operate in this region. So this is how torque of an induction motor operates with its slip or speed. The entire operations are divided in two zones. One is stable and other one is unstable. Now, moving to the next slide. In this slide, we will discuss the effect of rotor circuit resistance on slip torque characteristics. So here, we have plotted slip torque characteristics with different values of rotor circuit resistance. This first curve is for rotor circuit resistance R2. Then R2 is increased to R2 dash. And then R2 dash is further increased to R2 double dash. And in last curve, this R2 is increased to the value X2. So with increasing rotor circuit resistance, one thing we can clearly see that the starting torque of the motor continuously increases with rotor circuit resistance. And if the rotor circuit resistance is made equal to the rotor circuit reactance, then we can get maximum torque at the instant of start. Second thing, whatever is the value of rotor circuit resistance, the maximum torque is same at all rotor value at all rotor circuit resistance. So we conclude that the maximum torque has no effect on the value of maximum torque. And one more thing, we can see that by increasing rotor circuit resistance, we can achieve maximum torque at a corresponding higher values of slip, or we can say lower values of speed. So as the rotor circuit resistance is increasing, we are achieving the maximum torque at a corresponding higher values of slip. And if slip is higher, means this maximum torque is achieved comparable at lower speeds. And if this rotor circuit resistance becomes equal to rotor circuit reactance at standstill condition, or slip corresponding to maximum torque becomes 1, means this maximum torque is available at the instant of start. So this is the impact of rotor circuit resistance, which can be summarized as the rotor circuit resistance has no effect on the magnitude of maximum torque. Second thing, the starting torque of induction motor is directly proportional to the rotor circuit resistance. As the resistance increases, starting torque also increases. And if the rotor resistance is made equal to the standstill rotor reactance, in that scenario, we can get maximum torque at the instant of start. And the most important conclusion is by increasing rotor circuit resistance, we can govern the position of maximum torque. By increasing rotor resistance, we can achieve maximum torque at lower values of speed or at higher values of slip. This is all about slip torque characteristics of three-phase induction motor. I hope you enjoyed watching this video. Here are the details of the references which are used for making this video. Very soon, see you in next video. Thank you for watching this video.